Hello. Let us try to spend a little bit of time to solve one or two problems by variation method. So this one is one of our previous CSR net exam question. So here the potential energy of given system h cross square beta divided by 6m x power 4. Here m is the mass of the particle. Okay. So the trial wave function they are given psi of x equal to alpha divided by whole power 1 divided by 4 e power minus alpha x square divided by 2. This is the our trial wave function. So we know four steps. One is we need to find normalization condition. In this question, they are already given the normalization condition. That is alpha divided by pi whole power 1 divided by 4 is a normalization constant value. So no need to calculate first step. First step is already there. Second step, we need to find the what is the potential energy and what is the kinetic energy of the system, which means the total Hamiltonian of the system H equal to kinetic energy plus potential energy. So we already discussed the kinetic energy of the system H cross square alpha divided by 4m, right? So this is already known wave function, right? Gaussian wave function only. So if you want to see one more time, then I can go for previous problem here. Here. So if you try to calculate this Gaussian using Gaussian trial wave function, we can get the kinetic energy h cross square alpha divided by 2m. Okay. So no need to worry about that value. So that is already well known value. The next step is calculate the potential energy. So the given potential energy of the system h cross square beta divided by 6mx power 4, right? So here I use this h cross square. This is our given system, right? So I use this one. This is our trial wave function. This is our trial wave function. So this is constant value. The remaining term I write like this, right? X power 4 e power minus alpha x square dx. So they already given this formula. So if you try to use this formula, 3 divided by 4 alpha square. So then you can get this potential energy of the given system. Okay. This is the potential energy of the given system. So then write the total Hamilton of the system, the energy E equal to kinetic energy plus potential energy. This is the kinetic energy and this is the potential energy. Then minimize this potential, minimize this energy respect to the adjustable parameter. This is our adjustable parameter alpha, right? If you try to minimize this value, this energy with respect to this adjustable parameter, then you can get the alpha value, adjustable parameter value, right? See, alpha equal to b 1 divided by 3. Then try to put this alpha value in our energy equation. So energy equation already known that E equal to h cross square divided by 4m alpha plus h cross square divided by 8m alpha, right? In place of alpha, I used this alpha value, beta whole power 3 by 2 value. So this is what we got the energy, ground state energy of the given system. So these are all the simple problems. So in case if you observe clearly, whenever we discuss the variation principle is there, two type of conditions are there. So this variation principle E naught expectation value of energy trial wave function Hamiltonian trial wave function divided by trial wave function. So this is our fourth postulate, right? So if you observe this equation clearly, what we solved last two problems. Uh, so this is the completely this denominator value is the normalized. What happen if this condition is not normalized? When we are going to use this condition E equal to pi h and pi, when we use this condition. So suppose for example the potential energy of given system mgh is there, for example. So in case we can use this type of system. So bx power 4 is there, then we can use this type of system. So next class we discuss about this thing. So right now just remember this is just a normalized condition. So for we are using this one only the first case, not the second case of the variation principle. So here I'm using the first case. When we are using the first case, when we are using this second case, we will discuss later. Let us focus on one more problem, then we can understand how to solve these problems. You need to remember the four steps. One need to first step is on so guess trial wave function, then the try to solve this normalization. Then second step is the try to find the Hamilton of the system, and then calculate the minimize this energy in terms of adjustable parameters. Then we can get the adjustable parameter value, then substitute this adjustable parameter into this energies. These are the four steps you remember. So then you can solve easily. The second problem I took from the textbook, this uh, one of the important problem. So problem number 9.10, the problem, the page number the 257. This quantum mechanics textbook. The textbook is there. This is a Hamilton of the system. Potential energy of the system. This is the A Dirac delta function x. Okay. So where A is the constant, delta x is the Dirac delta function. Estimates the ground state energy of a given system using Gaussian railway. Most of the case, they are asking about the ground state energy. They are not asking about complicated like a first order energy. Next energy state, exited energy state of the given system using variation principle. So this is the one of the example. You look at this example, this potential energy is there. As usual, same the Gaussian. They are giving the Gaussian type wave function. If you look at this Gaussian wave function, here I'm using the in place of alpha beta. Okay, beta I use. So if you try to solve this one, so this is our next step is already Gaussian wave function they are already given. The next second step is calculate the Hamiltonian of the system. H equal to the kinetic energy plus potential energy. First, I try to calculate this kinetic energy of the given system. Okay, so if you calculate this kinetic and trial wave function, if I use trial wave function, then we can get this step. So these are the complete calculation of this. You try to differentiate this power minus beta x square into 2 times, then you can get this answer. Okay, substitute these values here, then you can get this equation. So here all the terms almost are cancelled. Then the remaining equations are the minus 2b and 4 also cancel. B we also cancel. Here b is there, plus b. Minus 2b plus b equal to minus b I got. So which one? Here already there, minus h cross square divided by 2m is already there in equation. Only this term I got. What is the answer? Minus b. So this answer is minus b. Remember this is already there in minus c. The next one is the try to calculate this potential energy of the given system. So if you try to calculate this potential energy of the system, see here. So you use trial Gaussian trial wave function, then you can get. So this is the Dirac notation. If you use x equal to 0 here, this term all equal to 1, right? So then only we can get 2b divided by pi whole power 1 divided by 2. Then arrange this kinetic energy, potential energy, the energy equation. H is equal to, this is the kinetic energy, this is the potential energy of our system. Then minimize with respect to V is our here variable parameter. Here the variable parameter is B. So then minimize this energy with respect to B. So these are the calculation steps. You want to look at this step by steps. Here it is already there. Then you can use these steps and calculate step by step. Then you can get p value. Then substitute this p value into, I mean, uh, into Hamiltonian. The given Hamiltonian. So equation number 1 is there already. This is equation number 1. So here I got b value, right? B equal to 2m square a square divided by pi h cross power 4 I got. If you try to substitute b value here and minimize this energy, then finally you can get this h is equal to minus m a square divided by pi h cross square. So this is our ground state energy of this potential. So remember, potential energy equal to minus a Dirac delta function. So these are the standard potentials. So to remember all equations. So like that, they are asking questions in CSR net gate examinations. So you need to focus this type of problem.